In this video, I'm going to talk about how to debug the animation selection by the motion flow system by looking at what cost various animations produce and by comparing it against the animations that you would like to be picked by the system. So let's first open the Visual Logger window, which is here in Windows, Developer Tools, Visual Logger. And then the next window we want to open is the FE Cost Debugger, which is under the same submenu. So now once you have both the windows available, we are going to hit record on the Visual Logger, and then you want to run your simulation. So let's do a few turns, and then let's try to do a dock. We'll do a vault over this higher wall, and I'm going to stop. So now if in the Visual Logger, if you click on this player controller track, this will be the name of your character that is being recorded. And if I scrub around, then you'll be able to see that you're able to visualize what the character did, and the system will redraw all the debug draws that were created during that simulation. If when you scrub, the character is not being updated, then what you need to do is go to your viewport, hit this triangle button, and enable real time, or you can press Ctrl R, which is a standard shortcut for this as well. The other thing to note is also the debug draw that happens, the debug print that happens. So down here you can see that the various costs and what the feature vectors the system has produced, or rather the feature vector fragment cost the system has produced, and different information like trajectory constraint has produced 3 samples. So each trajectory is comprised of 3 samples. So there are these 3 red spheres that we see over here. So what were the costs for each one of those? So we can look at that kind of information being printed over here. The other thing that you would note that each debug print, so let me make this larger so that we can look at the debug print in one go. So here you will see that at the top we have the contributor tag, which is combat jock. That is the name that you would provide to your contributor inside your graph, animation graph. So just to explain that a bit more, if you go to the blueprint for the character, I'm going to navigate there directly, but you can go through the content browser over here as well. So if I open the animation blueprint, let's say the mixed one over here, give it a second to open, and then any motion flow node you uses a contributor name here. So we have a local motion contributor node, and then we have a dock contributor node in this example. Or if you were using a bit more involved motion state machine, like so, here, then you might have each node named specifically with the contributor name over here, which you will see in the case that I just recorded over here. So if we make this dock again with the world, with the world displayed, so I'm going to put this over to the side here, and then let's find a place where the character is actually docking. So here at this moment, the character has made a search to go perform the dock. So there is a contributor for the combat jock because the character is still doing some locomotion. But if you scroll down, then there should be another contributor for the vault, which you see here. And the information followed by this contributor tag is the information that is generated by the search that was performed to do the dock. So for example, we used a pose constraint to do the search from the locomotion to the dock. And also we use a distance constraint to measure the distance cost and angle cost of what animation to pick when you're vaulting, using that vault 1.5 constraint, which is a 1.5 meter vault. And this is the information that the character is actually using while playing, for example, what kind of warping to do, and how is the current pose being generated. So this is some tick information that the character is using right now for this particular animation. And this is the tick information the character is using for the locomotion. So all the tick information goes together at the very end. So now let's say at a particular point of time, we can choose any example. If you wanted to find out why was this particular local motion animation picked, or we wanted to understand why was this dock animation used. So let's use the dock as an example, but a similar methodology can also be applied for locomotion selection as well. So what I'm going to do is find a point here, like once the dock has been initiated, and you will notice that in the FE cost debugger window, here are the contributors being displayed with the capture feature vector button that is available for each contributor. So combat jog is a contributor, or the locomotion state that the character is in. And then once you do the dock, then that vault 1.5 capture feature vector is also contributor is also available along with the capture feature vector. And then if you click on each one of these, it shows the exact pose that is used, that is produced by the nodes without any blending to the next node. And then if you click in the empty space, that shows the final pose that was produced, or final pose that was produced by the final blended state machine, or the final output that was set to the skeletal mesh of the character. So again, going back to the problem of why was this particular animation picked, so or like why was a particular animation not picked is something that we would like to interrogate the system with. So let's click this capture feature vector button. So after you click this, you will notice that this feature vector array gets populated. That will be the feature vector that was used at this search for the vault. So we'll click that, and then you see that it creates a 31 size feature vector, which happens to be the feature vector that was used. Similarly, we could have captured the feature vector for combat jog, which I'm going to do now, and that you'll see that's a 68 array. So that's a larger feature vector that gets used for locomotion searches. So I'm going to go back to select capturing the vault feature vector, so that changes back to the 31 array feature vector, 31 sized feature vector. And now we want to compare that with a different docking animation. So if you click this, your system should show what other animations could have been used. Now again, I'll capture the locomotion, the combat jog feature vector, and this will change to all the combat jog animations that were tagged with that same constraint that was used for the locomotion that was generated in this scenario. So let's go back to our vault, and then this should populate all the vault animations that were available to the search. So if you open that vault animation, now you can enter the time here exactly of what you want, or an easier way is to double click this animation. That will just open the animation in a persona editor. So let's say we wanted to understand why was this particular vault not used. So what you want to do is be inside the task search region if one is present, or if there is no task search feature present, then you need to be inside the task anim notify state. So in this region that is denoted by this task. But if again, to repeat, if the task search is present, you do want to be present inside there, because that's where the feature vectors are generated. So let's say anywhere here is fine, because the search is only done once inside here for the dock case. And I'll show very quickly how to do that for locomotion right after this. So what you want to do is click this button. So that will grab that time from the animation, which is 17.712 seconds over here. And then it generates the cost of picking that animation instead of the one the system produced. So if you look at what the system produced, it will scroll down and find our vault contributor, so which is here. And then we will see that the total cost for producing that pick was 64 versus 121. So now we have a further question to ask, like, was it the pose that was not matched well, or was it like the distance constraint that was not matched well? So if we look at the pose, the cost is 8.8, whereas the cost of the pose fragment here is 121. So there was a significant difference between pose. So you can, and then let's look at the distance constraint. So we see that the distance constraint actually was better over here, the fragment cost. So you might make a decision of, you know, hey, this looks like this, the angle cost here, or let's look at the size cost was actually better, but the pose cost was better over here. So you might want to change the weight of your pose inside your constraint fragments. Now I don't recommend doing that in this particular scenario because of the changes that we are going to do for distance fragments, because often the size and the pose fight against each other. Size is the distance between the character and the target, or the anchor point where the character is going to perform the task on, and then the pose is exactly the pose the character is at that moment. So you do want to match the pose, but you also want to match the distance, and these can compete against each other, because let's say if you were to go a little closer to the distance you wanted, but then your pose is drastically different at that point, so you don't want to pick that point, because then if you blend between these very different poses, then you will get a very kind of unnatural blend. So currently we have tuned for our data, we have tuned the weights so that let me bring this here so that I can see the content browser a bit better. So that the selections happen the way we want. So let me try to show you what the constraint weights are at right now, and where would you change them. So if you go to our characters, mannequin, and constraints, and then in this particular case we are looking at a vault constraint, vault 150. That's the task we are doing. And here under the fragments, we have two fragments, pose and distance exit. And under the sim, there's a weight assigned to the distance exit, which is 10. And under the sim here, there's a weight assigned to pose over here. So you can increase or reduce the pose weight if you want to pick a better pose. Oh, sorry, let me go back and let's look at the pose cost again to make that decision. So let's say you wanted to pick this fragment that we have, or this point in the animation instead of the one that was picked. So here we see that the distance was costed better, but the pose was costed worse. So in order to favor the distance, we are going to reduce the pose weight or increase the distance weight in the constraint. So what you would want to do is increase this to maybe, let's say 100, and reduce this, and or reduce this to 0.1. So you can try that to force the system to use this animation instead of the one that was used over here, and then we can probably see that happening, and if you were to do that change and run the simulation again. So this is how you can use the information being displayed and recorded inside the visual logger, and use the cost debugger to interrogate the system for why a particular animation was not picked, and then you can use those decisions to tune your weights or even understand coverage issues. For example, let's say another understanding that you can do from this kind of scenario is that, hey, I have an animation that matches quite well from a distance but doesn't match that well in the pose. So maybe you want to record more data or have your artist make more data that requires that produces less cost for your system. So you can also understand coverage issues by understanding the costs that were produced for each fragment and the constraint overall. So this is how you use some of the debugging tools that we provide with MotionFlow, namely the visual logger extension and the recording of the data, the debug data from MotionFlow, and the FE cost debugger window over here that helps you compare that cost with other animations that are available in the system. So as I promised, we will also do this very quickly for the locomotion side before I end this video. So let's go find this turn over here and capture this feature vector, and then let's try to see maybe we want to do directions plant because that's where the turns are. And over here now you'll notice the difference that there's just a task state here. There is no task search here. So what you can do is you can place your time cursor anywhere within this task region. So let's say we wanted to pick this turn that the character did right over here. So you can copy this time 81955 over here and enter it over here, or you can just press that button and that should grab that time. And then you will see the comparison of the cost between what the system picked as the best pick. So let's see what that cost was 33 over here, and here it is 195. And now let's look at the next level to see what was the cost. Oh, sorry, I wasn't properly scrolled in. The total cost was 453, not 195. 195 was just the post cost. The post cost over here, on the other hand, was almost zero. It was very close, or probably exactly zero, looks like, because it is probably playing the same animation continuously in this case. So picking this animation would actually be much worse. And if you look at the fragment cost for the trajectory, so that's also higher here, 64 versus 8.2, and the future trajectory is much higher here, 193 versus 25. In the future, in our future versions, we'll also display the debug draw associated with these costs over here in the world, so that you can see what trajectory that this picking this animation would have produced. Then you can visually also understand why was this particular animation not picked versus this. So especially understanding coverage, if let's say you did want your the red here is your actual past trajectory and the green is your desired future trajectory, and then in this case the cyan and the magenta color here is your data past trajectory, and then the cyan circles here, this first one, second one, third one, is your data future trajectory. So you can see that your data future trajectory that you want, the data future trajectory that is picked versus the green future trajectory that you want does not exactly match. So then you can go and capture more data that recreates this trajectory a bit closer. So that's how you can understand the coverage and locomotion, and you can further tweak the results or improve the results by putting in more data that you would want. If let's say this was the feature vector for the past and the future that you often produced in your game, then you would want to have data for something like this available in your system for it to pick. So this is how you can use these two tools to improve your data coverage and to tweak your weights of your constraints in the system. Thank you.